Hi, I decided to create an online course about Node.js. This is the first video in this course, and in this video I would like to talk about what Node.js is, what Node.js can be used for, and I would like to briefly explain how it works. Node.js is an asynchronous event-driven JavaScript runtime. Basically, Node.js is a program that runs your JavaScript code outside of the browser. It works like this. You write JavaScript code using the APIs provided by Node.js for things like reading and writing files, running an HTTP server, sending network requests, encrypting data, etc. Then you feed your JavaScript code to Node.js binary. And Node.js parses, compiles, and runs your JavaScript code and uses the underlying operating system's APIs to do tasks like input-output, running a server, etc. Basically, that's what Node.js is. It's a program that runs your JavaScript on top of the underlying operating system. So you no longer need a browser to run JavaScript. Also, Node.js is cross-platform. It works on popular operating systems like Windows, macOS, and Linux, and a number of other operating systems. And it's open source. Its main repository is hosted on GitHub. Now let's talk about the major Node.js use cases. Basically, Node.js is very useful for building non-CPU bound network applications. These are the applications that don't do heavy computation, but they can do a lot of input-output, like for example, database queries or reading and writing files. Basically, the most of the web applications fall under this definition. For example, let's say we are running a blog and there is a page that displays a list of blog posts. So what do we do to get the list of blog posts to the user? So the user requests this page, and our blog application, what it does is it goes to the database to fetch the list of posts and then simply returns this list of posts back to the user. It doesn't need to do any heavy computations to accomplish this. For example, it doesn't need to encrypt or decrypt a lot of data, or it doesn't need to process a video, etc. Just simply fetch the data from the database, which is an input-output operation. So usually Node.js is used for web servers like RESTful and GraphQL APIs. Also it is used for WebSocket-based applications like chats and collaboration apps. Node.js is used for build tools like Webpack and Rollup.js, and command line interface applications like npm, Prettier, and TypeScript CLI. And of course, Node.js can be used in other cases if it suits the requirements of those cases. Now I would like to talk in more detail about what Node.js is. Node.js is a C++ program. It is written primarily in C++ and JavaScript. Node.js executable, for example, when we run node and then we specify the path to the script, this node executable is written in C++. Basically, Node.js is a C++ program that runs your JavaScript. And Node.js provides JavaScript API that you can use in your code, like for example, the file system module that allows you to read and write files, crypto modules that allows you to encrypt and decrypt things, other modules like HTTP, path, net, etc. And at this point, I think it would be useful to note that it's the upper layer of the API that is written in JavaScript. Many API functions that we use actually call C++ functions under the hood. For example, when we call fs.read file in our JavaScript code to read a file, this function calls a C++ function that reads the file. And in the Node.js GitHub repository, there are two main folders where the code is stored. The first one is the lib folder. This is where the JavaScript API code is stored. And the src folder. This is where you can find the C++ code for the Node.js binary. Now I would like to explain briefly how Node.js runs our JavaScript code. Here, let's say we wrote a simple JavaScript program that imports the file system module and calls the readFile function to read the file called file.txt, and we expect the result, the content of the file, in this callback. Then we run this code using Node.js, and Node.js compiles and runs our JavaScript using the V8 engine, and calls the readFile function, and the readFile function calls the corresponding C++ function that reads the file. The C++ function uses the cross-platform asynchronous input-output API provided by the libuv library, and this API, the libuv, uses the operating system's API to read the file. The operating system then reads the file and returns the file data back to the libuv APIs, and the libuv returns this data to the C++ function, and the C++ function passes this data further up to the JavaScript read file function, which further passes this data to our callback function here. And finally, we can work with this data in the JavaScript layer. So this was a very simplified explanation of how Node.js runs our JavaScript code. Let's continue and talk a little about the V8 engine. V8 is Google's JavaScript engine. Primarily it is used in Google Chrome browser and Node.js. Node.js uses V8 under the hood to parse, compile and run JavaScript. It embeds V8 like any other C++ library and controls it using the V8's C++ API. So V8 parses, compiles and runs JavaScript. It enables C++ applications like Node.js to expose their own objects and functions to JavaScript, and it makes JavaScript objects and functions available to C++ applications like Node.js. V8 allows us to bind JavaScript layer with C++ layer. Now let's continue and talk a little about libuv. Libuv is a multi-platform support library with a focus on asynchronous input-output. It's written in C. Node.js uses libuv to access various features of the operating system. Libuv provides the famous event loop. The event loop is a mechanism that allows us to run code alongside asynchronous input-output operations in a single thread. The big picture looks like this. The event loop runs our code, and at some point our code does an input-output operation. This input-output operation is started using the operating system's asynchronous input-output API, and our code tells the loop, hey, call this callback with the result when it's ready, and then the code continues with doing something else. The event loop constantly checks in with the operating system to see if that input-output operation is ready. And if it's ready, the event loop calls the callback with the result of this operation. And our code can then continue processing the result. Together with the event loop, libuv provides a lot of features like the abstraction of non-blocking input-output operations across multiple platforms. Basically, you can write the code once and will be able to compile it for multiple platforms like macOS, Windows, Linux, etc. It provides the APIs for file input-output, DNS, network input-output, child processes, pipes, signal handling, polling, basically polling for asynchronous input-output, streaming, and a thread pool. You can find more details on its website, libuv.org. Okay, let's continue. You might have heard already that Node.js is single-threaded. But what does this mean? Node.js program runs in a single thread. It runs our JavaScript code in a single thread. So if we use Node.js as a web server, which is one of its primary use cases, all requests are handled in a single thread as well. What does it mean that Node.js handles all requests in a single thread? Node.js is an asynchronous event-driven JavaScript runtime. The keyword asynchronous means that Node.js allows us to do input-output operations, for example, reading and writing files and sending and receiving network requests alongside our JavaScript code, because Node.js provides us with non-blocking asynchronous input-output APIs. Node.js has the main thread where it runs your JavaScript code alongside the input-output operations. Also, it uses the thread pool provided by libuv for tasks that are CPU-bound, like encrypting data, for example. Libuv also uses the thread pool to offload some input-output operations for which it cannot or decided not to use asynchronous API of the operating system. One of the reasons for this could be that not all platforms provide a synchronous API for a feature, or the API is not consistent. For example, some operating systems provide a synchronous API for DNS calls and some don't. So libuv offloads DNS calls to other threads. Also the file input-output. Even though operating systems provide a synchronous API for file input-output, there are multiple cases where file input-output can still become synchronous, even when using a synchronous API. So file input-output is done through the thread pool as well. Next, I would like to explain what threads are and what is meant by blocking and non-blocking input-output. When you run a program, it turns into one or more processes that are managed by the operating system. Let's say we have a program, and when you run it, it turns into an instance of a program, which is called a process. And the program can have one or more processes. Let's say it has 2 processes. And it can have more. A process basically is an instance of a program, and it has at least one thread of execution, the main thread. And the process can create more threads if it needs to do 2 or more tasks together. A thread is a series of instructions for the CPU that are needed to accomplish some task. The threads share their process's virtual address space. For example, these 2 threads share the virtual address space of process 1, and these 3 threads share the virtual address space of process number 2. Basically, operating system provides a dedicated virtual address space to each process. Address space is the memory that a process is allowed to access. This is where the process's instructions are stored, and this is where the process can store its data. The processes do not share their address spaces. So thread from process 1 cannot access the address space of thread from process number 2. So there is no link between these. So process 1 cannot access the memory of the process 2, and vice versa. Basically, only the threads that belong to a process share that process's address space. Usually in our computers, a lot of programs run at the same time. So there are a lot of threads to run. And one CPU core can execute just one thread at a time. But in most cases, we don't have a dedicated CPU core for each thread. Let's say we have a computer with a single CPU, and this CPU has a single core. As I mentioned earlier, a single core can run just one thread at a time. This means that in our example, the operating system can do just one thing at a time. It cannot just throw all the threads to the CPU and expect these threads to be processed together. So all the time the operating system has to decide which thread out of all the threads to process and when. And the program in the operating system responsible for deciding which thread to run and when is called scheduler. This decision process can be really hard. If a scheduler decides to run threads one by one, such that each thread starts only after the previous thread finishes, we get a very unresponsive system. For example, let's say we start a thread that downloads something from the network, and this thread takes 2 minutes to get the data and exit. We have a thread, it downloads something from the internet, and it takes 2 minutes to process. And we have some other threads in the queue. So during the 2 minutes that this thread is running, we cannot run anything else. We cannot process any other thread, okay, while this one is running. And basically our computer becomes unresponsive. We cannot interact with it. For example, if you have some input from the keyboard, the threads that handle that input cannot process it because they are not running. Another program occupies the CPU for 2 minutes and nothing else can handle that signals. So to be responsive, the operating system gives control of the CPU to each thread for a given amount of time called a quant. For example, it can be around 10 milliseconds. This allows multiple threads to be able to do something concurrently using a single CPU core. Or even if there are many CPU cores like 2, 8, 16 or more, usually the number of threads is still greater than the number of cores. For example, my computer has just 2 cores, and at the moment I have around 350 threads running. Now our program that downloads something can handle the data from the network during these 10 millisecond quants, and other threads can use these quants to do their tasks and respond to various events as they occur quite rapidly. Now the CPU time is shared. Let me show you a more detailed example. Let's say we have 3 threads. Thread 1, thread 2, and thread 3. The scheduler looks at these threads and says, hey, I know that thread number 1 is the most important, so let's run it first for a quant. When the quant elapses, the control is returned back to the scheduler, and the scheduler decides to run thread number 3 because it thinks that it's the second most important thread. So it says, okay, let's run this one for another quant. Then the control of the CPU is given back to the scheduler, and the scheduler decides to run thread number 1 because it's very important for another quant. Then the control is released back to the scheduler, and the scheduler says, okay, thread number 2 hasn't been running for a while, let's run it for a quant. The control is released back to the scheduler, and the scheduler says, okay, let's run thread number 1 again, because it's very important for another quant, and the thread number 1 has finished running. The control of the CPU is given back to the scheduler, and the scheduler says, okay, now let's run thread number 3, because now thread number 3 is the most important. It runs it for a quant, gets back the control of the CPU, and says, okay, let's run thread number 2. It hasn't been running for a while. It gets back the control, and then runs thread number 3 for another quant, and the thread number 3 is finished running. And finally, the scheduler runs the thread number 2 for another quant, and the thread number 2 has finished as well. This is a very simplified example of how the scheduling works. And usually, of course, there are many more threads in the system, and usually there is always something to do. There is always a thread to run. Now it's important to mention that each time a thread is switched, there is a cost involved. The operating system has to remember where the thread stopped, so when it will run this thread again, it will start it from where it has been stopped. This process is called context switch. Here we have two threads, and the scheduler runs thread 1 for a quant, and then it needs to switch to the thread number 2 to run it for another quant. And this is what the context switch is. It involves remembering the context of the current thread and loading the context of the next thread. So each thread has its context, the state, and when threads are switched, their contexts are switched as well. Basically, the operating system has to store the thread's state and load the state of the next thread each time the threads are switched. The switch between threads of the same process is quite efficient, but the switch between the threads that belong to different processes is much less efficient, because those threads use different memory address spaces, and what was cached by the CPU for the previous thread will not be valid for the next thread, and the CPU cache cannot be reused. Now that we know what a thread is, we can easily understand what is meant by saying that Node.js is single-threaded. I have mentioned already that actually Node.js uses multiple threads. The saying that Node.js is single-threaded means that our JavaScript code runs and all event handling is happening in a single thread, the main thread. By event handling, I mean input-output. Things like processing chunks of files that we read, sending and receiving network requests, etc. Another example is when we start an HTTP server in Node.js, all requests from the clients are handled in the main thread. So let's say we have the Node.js process here, and it has the main thread. And all the requests are being handled in this single thread. Now let's say we need to query a database for each request. This is a network input-output operation. In other languages, like for example PHP, by default, when we run a network input-output operation in a thread, the thread cannot continue running instructions before the network input-output operation completes. This is what the term blocking input-output means. Therefore, in PHP, each request needs to be handled in a separate thread. So processing one request doesn't block all the other requests, as they can be processed concurrently using threads. So when we use a language like PHP, each request is processed in a separate thread. Because the input-output operations by default are blocking. And if we used just one thread to process all requests, and for each request we needed to run a database query, And if we have like 300 concurrent requests and we process those requests in the single thread, when we process request number 1, the other 299 requests have to wait for the network I/O of the request number 1. Then we process request number 2, it issues another network request to get data from the database, and the other 298 threads are waiting for this request number 2. So by the time we get to the request, let's say 250, the user who sent that request would become really angry, because they would have to be waiting for all those 249 requests, which can take like, let's say, maybe 10 seconds or 20 seconds, which is quite a noticeable time that you have to wait for a response, right? So because the input-output is blocking, we have to process each request in a separate thread, so we can process them simultaneously, and nobody will have to wait for a large amount of time to get a response. In Node.js, we have a different picture. Node.js does input-output operations asynchronously. For example, when we run a network input-output operation, for example, a database query, Node.js tells the operating system, hey, start this network input-output operation and let me know when it's done, so I can process its result. And then Node.js continues processing something else like other HTTP requests that it gets as a server. So if Node.js needs to handle 300 concurrent requests as a server, it can handle them in the same thread, because each database query is non-blocking, and therefore avoid the cost of spawning a huge amount of threads, which involves a noticeable cost. There is much more context switching, as we have like a lot of threads. Let's say we have 300 more threads to process 300 requests, and each thread occupies memory, and also managing multiple threads in a program is complicated, and this opens more possibilities for bugs. So Node.js handles all requests in a single thread. So when it gets multiple concurrent requests, like 1, 2, 3, let's say, and for each request, it needs to run a database query, which is a network I/O operation. So let's say it processes the first request. It tells the operating system to start running a network request to query the database, and it doesn't have to wait for this operation to complete, so it can continue processing the other incoming request, number 2. It does the same for the request number 2, and then continues processing request number 3, and so on. Then, when the data for the request number 1 is ready, Node.js can process the data for that request and send back the response. And the same goes for the other requests like this. So because of non-blocking input-output operations, Node.js can process multiple requests, multiple events in a single thread. So Node.js would be a good choice for a typical web application that does mostly network input-output like database queries. Node.js is able to run our JavaScript code and various input-output operations efficiently in a single thread, because it utilizes non-blocking input-output API of the underlying operating system. Now I would like to talk in more detail about blocking and non-blocking input-output operations. I would like to start by saying that with blocking I/O, it is easier to program. Let's have a look at a simple example of a blocking I/O operation. Here on the first line we get data from the database, which is a network I/O operation. Then we store the data in the variable data. Then we parse the data, and then we do something else. The operation on the first line is a blocking I/O operation, which means that we have to wait for this operation to complete before we can move on to the next line. And an input-output operation can take time. It can take, for example, 1 millisecond or 100 milliseconds, or it can take a couple of seconds, and so on. And the thread will have to be blocked for this amount of time before it can process something else. Commonly, in many programming languages, the instructions in the code are executed synchronously, one after another. When we reach an instruction that does input-output, we wait for the input-output to complete before moving to the next instruction. Here we have a very simplified example of a web server app that responds to incoming requests. We have an infinite loop, and we use this loop to be able to handle requests one by one. Here we grab a request, then we run a network input-output operation to get the data for this request from the database. Once we get the data, we send a response back to the client with this data, which is another network input-output operation. Then, if there is a condition that we need to stop the web server, we exit. Otherwise, we continue processing the next request in the next iteration of this loop. Here, we are waiting for this input-output operation to complete to be able to move forward to executing the next line. And the same here. The send response call is an input-output operation as well, and it can block the thread as well. The issue with blocking I/O operations here is the following. Let's say we have to process 1000 concurrent requests, and we start with processing the first request, here. While we are waiting for the I/O operations for this request to complete, the other 999 requests are waiting as well. Let's say that these two I/O operations take 100 milliseconds to complete. Now let's calculate how much time it will take to get to the request number 500. So it's 499 multiplied by 100 milliseconds, which is 49,900 milliseconds, or 49.9 seconds. And this is a really long time that you have to wait for a web page to load, right? And this is the issue that occurs if you process incoming requests in a single thread with blocking I/O. The popular solution to this issue is to process each request in a separate thread. This allows us to process a lot of requests concurrently. Let's have a look at another example here. In this example, we process requests using threads. Again, we have a loop. In this loop, we get a request, and then we send this request for processing to another thread. So this time we process each request in a separate thread to be able to handle many requests together. And this approach, of course, has some overhead. We have to keep a lot of threads and manage them, which uses additional memory and processing time, and as well introduces another layer of possible programming mistakes, as managing multiple threads and sharing resources between them can be quite tricky. Now let's talk about non-blocking input-output. Here we have an example of a non-blocking I/O operation. Here on this line we get the data from the database as well, but this time we use asynchronous I/O API. From this call we get a handle that references this I/O operation, and we can use this handle to check whether the operation completed or not. And if it completed, we can use this handle to get the data. Here in this while loop, we check if the operation completed, and if not, we do something while waiting. So we do something for, let's say, 20 milliseconds here. Then once this line returns, we continue to the next iteration of the loop, and again we check if our I/O operation completed. And if it is completed, we get true from this function call, and therefore we move out of this loop, and now we are able to get the data and move on. That's what an asynchronous I/O operation is. Basically, asynchronous input-output allows us to do something in the same thread while waiting for the result. So during such an input-output operation, the thread doesn't get blocked. While we are waiting for the result, we can still do something on the CPU. Let's move on. So this example shows how top-level asynchronous I/O API looks like in Node.js. In this example, we send an HTTP GET request to an HTTP endpoint. For this, we import the HTTP module. We create a callback function that we would like to be called when we get the response from the endpoint. Then we call HTTP GET method with the URL of the endpoint, and we pass the callback. And at this point, behind the scene, Node.js does something similar to what we discussed in the previous slide. Node.js uses an asynchronous I/O API to start our network I/O operation, and then once in a while it checks if this operation is completed, and if it is completed, it calls our callback. And all of this is part of the event loop. I will talk about the event loop later in the course. So on this line, Node.js starts network I/O operation and immediately allows us to process something else. And once this network operation is ready, Node.js calls our callback with the response. So to summarize, when using synchronous API for an I/O operation, we wait for this operation to complete before we can do anything else. But with asynchronous API for I/O, we tell the operating system to do the I/O operation, and we can do something else immediately while that operation is in progress. Then we can poll the operating system to check if the I/O operation is ready and get the result if it is. So, as we have learned already, in order to allow running JavaScript code together with input-output operations in the same thread, Node.js provides a synchronous I/O API. Basically, we tell Node.js to run an input-output operation and give it a callback function that we would like to be called with the result of the operation when it's ready. To support this scheme, Node.js uses a mechanism called the event loop. Basically, it's a real loop. This is an extremely simplified example of the event loop. So, while the loop is valid, Node.js runs our JavaScript code. Then, once the part of our JavaScript code that is running in the current iteration of the loop returns, Node.js moves on to checking if there are some input-output operations pending. For example, in our JavaScript code, we sent a request to get some data from the database server. In that case, Node.js started a network input-output operation and stored our callback for that operation. And on this line, it checks if that operation is ready. And if it's ready, Node.js calls our callback with the result of the operation. And then the next iteration of the loop starts. Again, Node.js runs our code if there is still something to run, and then checks for pending input-output operations. Once there is nothing more to process, and there are no pending input-output operations left, the loop ends and the program exits. This was a simplified explanation of the mechanics behind the event loop. Since everything here is in the same thread, we should not do heavy computations such as compression, image and video processing, etc., because these operations occupy CPU for quite long. While some computation is running here, Node.js cannot move on to processing the input-output. For example, if we use Node.js as a web server and we start doing a heavy computation for one of the incoming requests, we cannot process any other requests while that computation is running. So if this computation takes a couple of seconds or more, all requests are waiting for this amount of time. Basically, your server won't be able to process incoming requests in a timely manner, making your users unhappy. That's why Node.js is very popular for I/O-bound applications such as a web server that doesn't do heavy computations. Though if we still need to do a heavy computation, Node.js provides us with the APIs to do it either in a child process or a worker thread. So this allows us to run a heavy computation in parallel to the main thread. Now we have reached the end of this video and I would like to summarize what we have learned. Node.js is a program written in C++ which runs our JavaScript outside of the browser. It uses different great libraries under the hood, such as V8 for running JavaScript, libuv for cross-platform asynchronous I/O, and APIs for other operating system features. Node.js uses other libraries as well, such as LLHTTP for HTTP parsing, CRS for some asynchronous DNS requests used in the resolve family of functions in the DNS module, OpenSSL for cryptography, and zlib for data compression and decompression. Node.js includes JavaScript API. Basically, it's the Node.js standard library. Basically, Node.js is an intermediary between your JavaScript code and the operating system. Node.js use cases are non-CPU bound network applications such as web server and WebSocket applications like HTTP APIs, chat, etc., build tools, and CLI apps. Node.js runs our JavaScript and event handling such as incoming HTTP requests in a single thread, the main thread. The mechanism that supports running our JavaScript together with I/O operations in the same thread is called the event loop. Also, we learned a lot about how threads work and the difference between blocking and non-blocking input-output operations. So, I hope you found this video useful, and if you liked this video, hit the like button and subscribe. Thanks for watching it, and have a nice day or night, and see you next time.